So welcome back, students. In the previous video we talked about the wave theory of light, and then we used it to deduce the formula for refractive index. Mu is equal to sin A by sin R, and that is also equal to V1 by V2. And we proved that light has to travel slower in denser medium. And this is what people had known in the olden days too. But the corpuscular theory of light, propounded by Descartes and Newton, predicted that light had to travel faster in an optically denser medium. But that was against what was being observed. So wave theory of light gave the correct picture of light as far as this is concerned. Now we will go on to prove the law of reflection too. The previous video we proved the law of refraction, Snell's law of refraction. In this video we will talk about the law of reflection. Start with a plane wavefront, and so this is a reflecting surface, and let's say this is the wavefront. So this is A and this is B. So it is traveling in this direction. It's going to hit the surface here. Okay. So let's say this continues and it hits here. And clearly, but you see, but when A hits, B wouldn't have hit the surface. Why? Because the wavefront would have been like this. So the wavefront comes here and then it makes contact with this here. Okay. So this is A dashed and this is B dashed. So after A has reached the surface, it will get reflected and then it will travel back into the same medium. As it travels back into the same medium, the speed will not change. So if it takes 2 seconds for B dash to reach this position, then A dash will also travel the same distance after reflection, because B is going to the surface and A dash is going away from the surface in the same medium. So the speeds will not change and this length must be equal to this length. Right? So what I'm going to do is, like, if I take this as the length, then I put it here. Okay? So after reflection, this point would have created a wavefront like this. The wavelet will be like this. So this would have just reached here, and A dash would have reached here. So this I'll call this will call as B double dash, and I need to find where A double dash will be. Okay, right? So then I have to draw a tangent to this, so that touches this one. Okay, so this will be my A double dash. Every other point on the wavefront would have continued, hit here, and then made this travel back here. Then this would have come and continued here, and then made this travel back here. So that the total length of this travel, and put it this way, this travel and this travel will still be equal to this length, because all the wavelets are traveling in the same medium. I hope you understand this. And so this would be the normal to it, right? So this would be the normal tangent. So my wavefront would be something like this: AB, A dash to B, then it will become A double dash, B double dash, like this. Then B double dash will just start taking off from that point. So this would continue like this. from that point forward, so you will have something. Okay. So AB came, it hit, and it's going to take off like that. I'm just talking about a time at which it is just taking off. Okay. Now let's see. Let me draw a normal here. Okay. And if this is a normal, this is going to be the incident angle, and this is going to be the angle of reflection. And we know this is 90 degrees, and this is 90 again, because this is 90 plane wave, and we know that this has to be 90, okay? And we also know that this has to be 90. All this we know. I'm going to call this as angle X, and what would this angle be? That would be I. We've done that before, because notice here, I plus R plus X is 90, I plus R plus X is 90 degrees, and then Rx and this angle will be equal to 90, this 90. Rx and this angle will be equal to 90. So this angle must be I. Now, let's see what happens. Well, this is X I said, but look at this. This line and this line, they are intersecting, which means this angle and this angle must be the same. And what would that angle be? That will be 90 minus X. Why? Because I can consider this as a triangle. This is 90, this is X, this must be 90 minus X. If this is 90 minus X, this must also be 90 minus X, resulting in this angle being X. This angle being X. Right? Because this is 90 minus 6, this is 90 minus 6, this is 90, this is 90. So this is X, this must be X. Okay? And now, I'll call this angle is R1. Okay? Let's see. If I take this triangle, A dash, A double dash, B double dash, this triangle, A dash, A double dash, B double dash, triangle, A dash, A double dash, B double dash, this is 90 degrees, and this angle is I plus X, I plus X plus R1. I plus X plus R1 is equal to 90 degrees. Compare this. I plus R plus X is 90. I plus X plus R1 is 90, which means if we take this as 1, if we take this as 2, then R1 must be equal to R. So this R1 must be equal to this R. So I will remove this. Okay, now this angle R1 is equal to R. If I prove that R1 is equal to I, then I must be equal to R. So that is actually the law of reflection. So that's very easy to prove. Look at this. Look at these two triangles. Okay, these two triangles. Length A dashed, A double dash is equal to B, B double dash. And then A dashed, B dashed is common for both these triangles. I am taking this triangle and this triangle. triangle. So A dash to B dash, A dash to A double dash, and B double dash to B dash, they are equal, and A dash to B dash is the same side for both of them. And notice here I have the opposite angle 90 degrees here, and here also I have 90 degrees. Okay, so this length must be the same as this length. They complement. You can very easily prove that. This length, which means that all the angles must be the same. You have 90 here, then you have I plus x here, then r1 plus x here. This angle and this angle must be the same. So I plus x is equal to r1 plus x, and you also have 90 degrees, right? 90 degrees there. Okay. So which means that I must be equal to r1. If I is equal to r1 and r1 is equal to r, then I must be equal to r. So the angle of incidence is equal to the angle of reflection, and this is a law of reflection. So by using the wave theory, you can very easily prove the law of reflection here and then the law of refraction in the previous video. So using the wave theory, you can theoretically prove the law of reflection and the law of refraction. You don't have to do even experiments. The experiments will only confirm this. So theoretically, without doing any experiment, just by doing mathematics, you can arrive at these two laws. So this gives you the theoretical background of the law of reflection and also the law of refraction, Snell's law. So this is very powerful in that respect. So people started taking this seriously after they were able to prove these two laws using the wave nature of light, the wave theory of light. We can actually use this wave theory of light to prove the refraction that takes place through prisms, through lenses, and even through the reflection that takes place through mirrors and stuff. Okay, it is very easy. Let me just take the triangular prism and then see how light bends after refraction. So this is the triangular prism. I'm going to take. Okay, so let me take a plane wavefront. Okay, again, the plane wavefront. This comes in here, here, okay, everywhere. Could be small, big, doesn't matter. So this is how I'm taking it. Okay. So what happens now is, let me take this point. Okay. Let's see what happens when the wavefront hits here. Like this point, when this point reaches here, then it will start traveling inside the prism. So this will slow down. The wavelet formed by this secondary source will slow down here. But then at that time, the wavelet formed by this secondary source will still be traveling in the same medium. This is medium 1, this is medium 2. Okay. So this won't slow down, this will continue to move with the same speed. Let's suppose this is made of glass, and that's why I'm using the word, I use the phrase slow down here. So it hits here, and from this point forward, like this is going to slow down, but this will continue till it reaches here. And this will continue till here, and it will continue to go. So there is a certain time, let us suppose, that this takes to reach here. and called it as tau. This time, the time it takes to reach here. But in that time, what would have happened to this? This would have traveled a little bit of distance in the same medium, but after that, when this wavelet travels so much, this would travel less. Okay, and in that process, this would have traveled only here. Okay, it would travel more than this in this medium, but then this traveled more in this medium, right? So this will travel like this. You notice, if this is my A and this is my B, and this will be my A dash, this will be my B dash, and now as it reaches here, this will be my A double dash, and this would be my A maybe. Okay, this will be my B double dash here. Okay, or if this is C, then this is my C dash, and this is going to be my C double dash. Notice now I'm going to have this kind of a wavefront. You see, my wavefront is bending now, like that. Now, as it comes out, again, it will take certain time to travel this. That's right. And in that process, if it travels this distance, this will travel a longer distance, right? Within that time from here, because it's already there, so it would travel a longer distance here. So it would be somewhere here. Okay, draw that. Okay, maybe if I draw this, whatever, something like this, and this would be like this, and this would be somewhere here like that. Here. Okay. So if we join all these, so this is going to be my new wavefront. So this will be my A triple dash, and this will be my C triple dash, my B triple dash. Notice here, so this, the ray, the waves, as they came here and they started bending, they give you the appearance of bending. So this, as they continue, and will go like this. Okay? So you can see that it is bending. The same thing will happen with the lens. Take this. Okay. So now there is this plane wave. So this is A, this is B, and this is probably C. So this comes, it's here, maybe this is there, and this one, that's it here. Okay, fine. At this point, as C enters that medium, so this is going to be my C dash, and this will be my A dash, and this will be my B dash. But then C is going to be slowed down inside. Then they will continue to move this way. Outside. And every other point here would be slowed down. But they will take a little longer time to get into this medium. But I'm just talking about this point. Okay? So now this would, what would happen here? This would take some time to travel through this. Because this is again made of glass, so the speed will be lower than this one. So this will travel less distance, whereas this will travel a longer distance here. So if you think about it, then I'll have something like this. Okay? So that's a wavelet. And again, this may have a wavelet like this. Okay? And you see this, again, after while they are doing this, then you may have a wavelet could be something like this in this time. So you see, then if I draw a common tangent to all that, I'll see like this. You notice that, like this point is now somewhere here. And like this, you see, then you start getting image. Again. Like this. This will be the point. Yeah. So this will be the point. So this will be the point. So if you join this, you see they give you the appearance of converging. You can do that. And you can do the same thing for a mirror too. So you can clearly see that they give you the appearance of converging. But the point is, so this is creating a wavelet everywhere. This is also creating a wavelet, and then it's a wavelet. But then you need to draw a common tangent which touches everything. So this is what you will get. So it look like now A dash has become A double dash here, and then this becomes C double dash, and this has become B double dash. Notice that you can see that it's kind of converging. So as they continue to move, then like they'll converge at a certain point. So this is how you can explain why a lens, a biconvex lens or convex lens, converges the light at a particular point. You can see this happening. And why does a prism bend light? You can see that happening. So at this, it all depends on the common tangent. Okay, but if you just take this, for example, if you just take this point, then this is going to create a wave. That's all. It will create its own wavelet. It will be like this, and this will create its own wavelet like this, and this will create its own wavelet like this. Okay, so irrespective of what the other things do, but you can show. But then the common tangent, which touches all of them, becomes a new wavefront. So now A double dash becomes A triple dash here, even though A double dash value is everywhere, but this is where the common tangent touches this wavelet. So now that becomes A triple dash. Again, the common tangent touches this wavelet here, so this becomes C triple dash. So C double dash has become C triple dash here. So the common tangent is important. But from that point, from the point source, the wavelets propagate. But the wavefront is the common tangent of all these secondary sources. So you may say A double dash is present everywhere. Yeah, but for wavefront, you will take only the point where A triple dash, the common tangent, touches this wavelet. So that is important for you to remember. The common tangent, and that becomes the wavefront. Because if you take the wavelet, it will go everywhere. How do you know the wavefront? Take the common tangent. So every other point, say this point would have also created something like here, and then this point. So all these will give you the appearance of bending. So the prism gives you this appearance. Okay, light comes, okay, goes, and then it bends like that, just like that. So this kind of appearance is not correct. Okay. And here, light comes, and then it gives you parallel lines. It gives you appearance of converging here. And then you see it continuously converging like this. So this is a wavefront. So this is the wavefronts are like this, wavefront come like that, and then they converge like this. They become the successive wavefronts after refraction. You can do the same thing for mirror too. Okay. So the wave theory of light explains reflection, diffraction, why light bends, and the relationship between the incident angle and then the angle of reflection or the angle of diffraction perfectly. And it says that it is all happening because of the difference in the speed of light in different medium. Hope you understand this. The next thing we are going to talk about is the Doppler effect. Since light is a wave, we can experience Doppler effect in the case of light. We studied about the Doppler effect in the 11th standard. And the example that we took was the sound wave. We said, when we were discussing that in the 11th standard, you can see different pitches, different sounds when a car approaches you, when you are standing on a platform, and when the car recedes from you, when it goes away from you. So these two sounds will be different. And also, if you are sitting inside the car, and when you are traveling on the road, then you will hear a different sound from the car. So all these sounds will be different. And this is because the sound wave undergoes Doppler effect based on where you are standing and what's happening, like whether the source, in this case the car, whether it is receding from you or approaching you. So we said, let me just quickly recapitulate what we did in the 11th standard so that we will be able to understand what happens in the case of light also. Okay, so suppose you stand here. This is your place, this is where you stand. You are the observer, and here is the source. This is a car. Okay. So this is the car, this is source. And this source is moving towards you with a speed of say Vs. So that's the speed of the source. And both of you are surrounded by a medium. So this would be air around you, right? So this is air here, everywhere, air. So this is the source. This is the source. I use a different color. This is the source, and this is the observer. And around you is the medium. And the source is approaching you with a velocity Vs. And it's going to generate its own sound, right? Maybe like someone is honking, or you are able to hear the sound of the engine itself. So when this source is at this position, it's going to let out, a cycle. Okay? So this sound wave will travel this distance to reach you. And how will it travel? It will travel not with this speed, but with the speed of sound in air. Once the sound wave is out of this, then it's going to be the medium which will take over. Right? So because the sound wave will travel in air to reach you. So it will reach you first before this reaches. So this will be the V of the speed. The speed of this wave is V. Vs is the speed of the source, and V is the speed of the sound wave in air. Okay. So this will reach you, but this will travel this distance, this length L, to reach you. So it will take certain time T. Okay. So let's say we take T1 to reach you. And let us suppose that in the time T1, since this is the source is also moving in this direction, the source will now be here. Let's use this. The source is now going to be here. And when this source at this position, when this releases the next cycle, then that will travel this distance. Note that the first wave had a certain distance to travel, so it will take a certain time t1. But now the second wave has a smaller distance to travel to reach you. So this will take a different time t2. So in this case, t2 is smaller than t1. If this was stationary, the first wave will take t1. The second wave will also take t1. The third wave will also take t1 to reach you if this was stationary. So this frequency will be the same as this frequency if this was stationary, because the time gap between the pulses will be maintained here also. Yeah, the first pulse will take some time to reach you, but then the next pulse will also take the same time to reach you. So whatever time difference exists here will exist here. So whatever frequency this is produced, you will receive it in the same frequency. But if the source is moving towards you, what happens is that the first pulse will reach you in t1 seconds, and the second pulse will reach you in t2 seconds, and then the third pulse will reach you in t3 seconds. In this case, t3 will be smaller than t2, which in turn is smaller than t1. You can see that this time gap is not maintained here. So the first pulse will come after some time, and then the next pulse will immediately come. You see, and like this is going to have a different frequency than this. So it's going to have a greater frequency, a larger frequency than this one, because the waves are crunched here. So like all these cycles, all these the pulses will reach you in shorter time. So it will look like you are experiencing higher frequency. And the opposite effect takes place when the source moves in this direction. When the source moves in this direction, then the first pulse will take t1 time to reach, and then the second cycle of the pulse will take t2 time. But then notice here, if it is moving away, then if the body is here, then the second pulse has a longer time to travel in this medium. So since it has longer time to travel in this medium, longer distance to travel in this medium, it will take a longer time to reach you. So the gap between the first pulse and then the second pulse and then the third pulse keeps increasing. So it will look like you have a smaller frequency here. So when this is moving, when it is approaching, this is how you feel. But when the source is moving away, then this is how you feel. So, but this is producing these waves at the same frequency, but at a certain frequency. But when the source is moving towards you, it will look like the waves are crunched in time, and when it is moving away from you, the waves will appear to be elongated. Okay, they are spread out more in time. So you will have less frequency here because the time is more. You will have a greater frequency here because the time is less between one pulse and the next pulse. But in both cases, you won't hear the same frequency. So the sound will appear different to you. And that is why when you sit inside a car and then move, the sound produced by the car, you will hear it with the frequency that it is producing. Because you are stationary with respect to that car. Because your speed and then the car speed both are the same. So you will hear the frequency that the car produces. But if you are on the platform, if the car is approaching you, then you will hear a different frequency. You will hear a different sound. That sound is not the same as the sound you hear when you are inside the car. And when it goes away from you, again you hear a different sound. And that sound is not the same as the sound you hear when you are sitting inside the car. So that's because of the Doppler effect. Okay. So the frequency is given by this expression. I am not going to derive the expression now. But I just wanted to give you a quick overview of what Doppler effect is. So the frequency, if you refer to your 11th standard. If the source is moving away, the new frequency f is equal to the frequency that this generates, the source generates, into 1 minus speed of the source divided by the speed of the wave in that medium. The source is moving away. You can see that this frequency is smaller. Why? You have a negative sign. This is going to be f0 minus f0 Vs by V. So this is going to be less than 1. So this frequency, as it is moving away, will be smaller because the time period increases. Likewise, when the source is moving towards you, then f is given by f0 into 1 plus Vs by V. So this is going to be greater. Okay, this f0 is the frequency of the signal, the sound that this produces, and f is the frequency you hear. So this is how it's given. You can see that. In this case, you can see that f is smaller than f0. In this case, you can see that f is greater than f0. So the same thing happens to light. Okay. Actually, let's think about it. Let's think about it. I've done it like this, right? Like the source is moving away from you. Okay. Let me take this case. Okay. I have the source here, or I am the observer, whatever. Okay. I am the observer. This is I am the observer. And let's say the source is moving around me in a circle. Okay. So this is the source. The source is moving around me in a circle. What is going to be the Doppler effect? Will I have any Doppler effect here? No. Why? If it is moving around me in a circle, even though this is moving, you see the distance between the observer and then the source is always a constant. So the first pulse will take certain time to reach me. The second pulse will also take the same time to reach me. The third pulse will also take the same time to reach me. So whatever frequency I produce this wave is the same frequency I will hear. What frequency? Okay, I just got it the other way. This is the source, and this is the observer. Then when this produces the first pulse, it will take a certain time to reach me. Then when it produces the second pulse, it will take, it's going to be here, right? Maybe it produces second pulse when it is here. But then that also takes the same time to reach me because the distance remains the same. And the third pulse it may produce when this is here. And that also will take the same time to reach me. So this produces a pulse, the pulses at a different time interval, at a certain time interval, and I will see those pulses in the same time interval. Okay, so the frequency will not change. So even though the source is moving like this, even though there is movement, there is motion of the source, I don't hear a different frequency, I will hear the same frequency. When will I hear a different frequency? When this is either moving towards me or moving away from me. Or in the relative scale, the source could be here, the observer could be moving away or towards. Doesn't matter, right? If something is moving away from me, it's the same thing as I move away, I moving away from that thing. So relative. So I can consider myself to be at rest and I can assume that the source is moving. Or I can say that the source is at rest and I can consider that I am moving, either away or towards. It depends on my perspective. So I've just taken this perspective. I've chosen this perspective where the observer remains stationary, the source is moving. I could have done it differently. Source remains stationary, the observer is moving. Both are pretty much the same. Okay, so likewise I can have a source here, I can have an observer here. Or I can have the observer here and then the source here. But the logic is the same. The relative speed is what is important for us. So when will I have Doppler effect? When this distance changes. If it is going in a circle, it doesn't matter. Even though it is in motion, it maintains a constant distance between itself and me. So the frequency will not change. But when the distance between the source and the observer changes, then I'm going to experience the Doppler effect. Okay. So I would say this is not the tangential speed that counts, but the radial speed. So the radial speed is what is important. Only then the distance increases. Only then can I experience the Doppler effect. Okay? So this is what we are going to do here. So likewise, just as happens in the case of sound, it happens in the case of a light also. When a light source approaches you, for example, there is a distant galaxy, and when it approaches you, then clearly that light you are going to receive at a different frequency than it was being produced by the source. For example, when it is approaching, then the frequency is going to increase. If it is going to increase, then you are going to see the light as a different color. For example, you see the colors, right? You have a GR. Okay, so this is high frequency highest, and this is going to be low frequency, right? When the star is approaching you, all the colors will try to get a different frequency, a higher frequency. For example, if you look at the yellow light, then it will kind of, even though the star produces yellow light, then it will look like it's either green or blue. Or even if it is going to remain as yellow itself, you will see a different frequency of yellow, because you see yellow as a range frequencies. So a bit of yellow, like if suppose it was produced in some frequency f1, but now you will receive it as yellow at a different frequency, because you have a certain range, right? So this frequency, even if it is yellow band, this frequency will look like this frequency. So there is a shift in frequency because the source is approaching you. As the source is approaching you, then the frequency is going to increase. So the frequency, the original frequency is getting shifted towards blue, the blue color. So you call this as blue shift. Blue shift does not mean that all the colors become blue. Okay, the colors are getting shifted towards blue. That is what blue shift means. Likewise, when this source goes away from you, there is a galaxy that goes away from you, then the light that you receive from it will tend towards red. It doesn't mean that everything has become red. Again, if you take yellow, the same yellow, and that would go towards this. So if this is at one frequency, the yellow that you receive would be at a lower frequency. It may still remain yellow, but yellow of a lower frequency. Or it could have even become orange. Or it could have even become red, depending on how fast it goes from you. Depending on the speed clearly the frequency is going to change. You can see that, right? So when it is going away from you, the spectrum, the light spectrum, is shifting towards red. So you call it as red shift. So if there is a light object, if there is a galaxy, if it goes away from you, then you sense it to, you call that as red shift. If it comes towards you, then you call that as blue shift. Okay? And this is how we are able to say that the universe is expanding. Because when you look at all these galaxies around you, like most of the galaxies you see, they all seem to be going away from you. And this is how you also understand the Big Bang theory. Why do people say that the universe once started from one common place and the Big Bang took place and everything started moving? Because when you observe the universe, everything seems to be moving away from you. Every galaxy seems to be moving away from you, for the most part. Okay. So you conclude that if everything is moving away, then at some point in the past they should have been closer. And maybe there was some point in the distant past they were all together at one place. And from there, maybe there was an explosion and things started moving away. So the Big Bang theory is proposed based on what you observe from the galaxies. And how do you know that a galaxy is moving away from you or coming towards you? Just by looking at its light. If you keep seeing that the frequency is changing towards red, then you know that the galaxy is moving away from you. If it is changing towards blue, then you say that the galaxy is coming towards you. And when you look around you, then everything in the universe seems to be going away from you. So you say the universe is expanding. And if it is expanding now, at a distant past, these things should have been together. So you also conclude that there was a Big Bang. Okay, that's how you conclude this. Okay, now let me get back to this expression. So I can take either one, either this or that. Let me just take one, okay, it doesn't matter. So let me take the first one. Either way I'll get the same result. I said F is equal to F naught to 1 minus Vs by V. This was for sound. But if I were to do it for light, then how will this change? So this will change to the new frequency F is equal to old frequency into 1 minus, what is Vs? Vs is the speed of the source, a galaxy, a star, or whatever. And is it just any speed? No. You have to worry about the radial speed. It has to go either away from you or should come towards you. So I call this as VR, which is the radial speed, which moves radially away from you, okay, or towards you. And what is V? V will be C, right? So that will be the velocity of the wave in the medium. That is V. In the case of air, sound and air, it will be 345 meter per second or something. Okay. But here it's going to be 3 into 10 power 8 meter per second. So that is how light travels in vacuum. So this is the velocity of light in vacuum, and this is the velocity of the source. It could be a star or anything, okay, or a galaxy or whatever. That is moving radially either towards you or away from you, and that is the speed of the source. And this is the speed of the light in vacuum. So this is what you get. Okay, I told you that it's moving away. If it is moving away, what do you say? Your F will be smaller than F naught. Okay, so let me if F is smaller than F naught, then what is my final? My final frequency is F. What's my initial frequency? F naught. So what's the change? Final minus initial will be delta f. Okay, so delta f is equal to f minus f naught. So this is going to be a negative number. Why? Because this is smaller and this is greater. So f minus f naught will be giving me a negative number. That will be the change. Okay. So f minus f naught. Final minus initial. Let me do it here. So this, if I expand it here, take it expanded here, f is equal to f naught minus f naught VR by C. Let me bring it here. So f minus f naught is equal to minus f naught VR by C. But what is this f minus f naught? That I said is delta f from here. It's delta f. Delta f is equal to minus f naught by into VR by C. I bring it here. So delta f by f is equal to minus VR by C. So that should make sense to you. So because in this case delta f is negative number, you get this negative. Okay. And finally delta f by f, this negative and this negative will cancel, and delta f by f is what you will get, you know, the absolute number. It's going to be equal to VR by C. So this is a very important expression for Doppler effect. So the change in frequency divided by the original frequency f naught, is equal to the radial distance divided by the speed of light. The radial speed of the source divided by the speed of light. Okay. So this is about the Doppler effect. So Doppler effect happens in the case of waves, because depending on how the source is moving relatively from the observer, the frequency could change. The frequency could appear to get big, to get bigger or smaller. Okay, so that is Doppler effect, and it can happen to sound, to light, to any wave. The Doppler effect would happen if the source and the observer are in relative motion to each other. Again, when we talk about relative motion, we don't talk about motion like this. We talk about motion in the radial direction. Okay? So the distance shouldn't change. If the distance changes, then the frequency that is produced by the source will be observed differently by the observer, and it's governed by this formula. I hope you understand. Do an example problem now. The example is 10.1. What speed should a galaxy move with respect to us so that the sodium line at 589.0 nanometer is observed at 589.6 nanometer? Okay. So don't worry too much about the sodium line part right now. Okay. You have to be focused on the wavelengths. Okay. So this is a technique they use to find the shift in the wavelength or the frequency. Okay. So let's ignore that for the time being, and let's focus on the rest of the problem. So what it says is that this light of this wavelength is changing to light of this wavelength, 589.6 nanometers. 589.0 nanometer is changing to 589.6 nanometer. The wavelength is changing. So if this is how it is, this is actually the original wavelength, and that appears to be changed to 589.6 nanometer. So if this is what is happening, then what should be the speed with which the galaxy must be moving away from you? Okay. Where did it say moving away okay, move with respect to us. That's what we'll see. Correct? Clearly, there is something that you can figure out straight away. The wavelength, the original wavelength is 589, the new wavelength is 589.6. So the wavelength has increased, which means that the frequency has come down. So you have a lower frequency now than what is produced at the source. So if the frequency becomes lower, smaller, then what does it mean? It means that the source must be moving away from you. You are shifting towards red. So red shift is what you are observing. So the galaxy is moving away from you. Okay. Now what do we know? The equation, the expression that we derived was this. So delta F minus divided by F naught is equal to minus V radial divided by the speed of light. This is what we did. So delta F is what you need to find. What is delta F? Delta F is final minus initial. Okay, final minus initial. Okay. But they are given me only this. The wavelengths, lambdas are given. Okay. What is delta F? Delta F is actually F minus F naught. But I don't have F minus F naught. All I have is lambda naught and then lambda. So lambda naught is 589 nanometers and lambda is 589.6 nanometers. So I need to, but I have only this expression. I need to express this in terms of lambda first. Okay. And what do we know? I know that C is equal to F lambda. Okay. The final frequency and the final wavelength, or the observed frequency and then the observed wavelength. And C is also equal to the source frequency and the source wavelength. Both are right. Okay. So can I express F in terms of C and lambda? So this gives me F is equal to C by lambda, and this gives me F naught is equal to C by lambda naught. So can I find delta F? So delta F is equal to F minus F naught, and that is equal to C by lambda minus C by lambda naught. So can I take LCM? C into lambda naught minus lambda divided by lambda to lambda naught. So F minus F naught is lambda naught minus lambda. Okay, so what is this? This is actually equal to minus C into, why minus? Because delta F is F minus F naught, then delta lambda must be lambda minus lambda naught, so I am taking minus out. So this is going to be delta lambda, where just in line with this, delta lambda must be equal to lambda minus lambda. Just like delta F is F minus F naught, delta lambda is also lambda minus lambda. See, minus C into delta lambda, so divided by lambda to lambda naught. Okay. Now, I need to find delta F by F naught. So delta F by F naught is equal to minus C delta lambda by lambda to lambda naught into f naught. What is f naught? F naught is c by lambda naught. So that's going to be c by lambda naught. So that lambda naught will go here. C will cancel. C will cancel again. So I'll get lambda naught and lambda naught will cancel. So I'll get minus delta lambda by lambda. Okay. You see delta by f naught is equal to minus delta lambda by lambda. But you know this also is approximately equal to minus delta lambda by lambda naught itself, right? So you see there is not much of a difference between this lambda and this lambda. 589, now I'm between 589.6 nanometer. Why do I do that? Because it's in denominator. Like if it is in addition or subtraction, it's a different story. But here it's in denominator. Okay. In denominator, dividing this by 589.6 is the same as dividing it by 589. So instead of dividing it by 589.6, I can divide that by 589. Pretty much the same value. So that's why I am approximating it. So ultimately, I am getting this expression. So delta f by f naught is equal to minus delta lambda by lambda naught. Okay. So this is expression 8. What I have done is I have expressed this in terms of, okay. Or the other way to do it would be, if you don't want to do it this way, simply convert that into frequency. So they have given you lambda, so find f naught and then f and use this expression straight away. You can do it that way also. Okay. So this is what is given in the textbook, so I wanted to explain this to you. Why they got this expression? They got this expression because of this. Okay. Otherwise, they've given you lambda, find f, find delta f, then do this. You will be fine. You don't need to worry about it. Okay. I've done it because it is there in the book. Okay. So once you know this, then the rest is easy. So minus delta naught, you know that minus delta naught by lambda naught is equal to minus VR by C. So this and this will cancel. Delta lambda by lambda naught must be equal to VR by C. So what is delta lambda? Delta lambda is 589.6 minus 589, so that will be 0.6 nanometers. So this is going to be equal to, I'll say, delta lambda by lambda naught is equal to 589.6 minus 589 by 589. 589.6 doesn't matter. Okay, so this is what you do. So that gives you 0.6 by 589. And you know that this is equal to VR by C, the radial speed of the galaxy divided by what is C? C is 3 into 10 power 8 meter per second. Okay, nanometers will cancel, you simply you have the ratio. So now what is VR? So VR is equal to 3 into 10 power 8 into 0.6 by 589. Well, let me make this as 600. So if I make it as 600, then 3 into, I need to multiply by 1000, right? So 1000, 3 into 10 power 5 meter per second into 600 by 589. So this is close to 1. 600 by 589 is close to 1. I mean, so like it's I can treat this to be number 1. Okay. So that gives me approximately 3 into 10 power 5 meter per second. If I convert that into kilometers, so that's going to be my radial velocity is going to be roughly 300 kilometer per second. So the galaxy is moving away from you at this speed, roughly 300 km per second. I think your textbook says it's 306 km per second, and that is because you do the division properly and multiply when you get 306 km per second. This is how we do it. Hope this is clear to you.